Yeah. Luca, you start it live stream then.
Yes, 1 second.
Yeah.
You can also put on video, Sujata.
No, my voice gets very bad if I put on the video.
Okay.
So I don't want to. I mean, the band is not great. Yeah.
And now you can start.
Yes.
All right. So welcome, everybody. Good morning, good afternoon, good evening to whichever part of the world you're in right now. But it's great to see Winnie virtually. I'm sorry, Winnie, you can't see me. But these are bandwidth limitations. You'll have to choose between hearing me or seeing me. So it's great to have this trimester. It's been going on for quite a while. And it's a pleasure to welcome Winnie Lee, an old friend. In fact, she just reminded me that 10 years back, she was in India and that's where we first met. Well, physically, otherwise, virtually we had been in touch and so on. So she's going to give the first talk on modular forms. So all yours, Winnie.
Thank you. Thank you very much for the introduction. It's a great pleasure to speak in this seminar. I would like to thank the organizers for the invitation. Okay. The purpose of this talk is to give an overview for modular forms, on modular forms for finite index subgroups. So I've seen that this is old topic, and naturally this topic shows up in the many previous talks. So let me still try to begin. I would like to. What? Let me just start from the very beginning. Start with modular curves. Okay. I know that the Tuesday's talk, its title is on modular curves, so there will be a short overlap with that talk. Okay. So the group SL2Z acts on the Poincare plane by fractional linear transformations. So we take a 2x2 matrix, ABCD. It takes Z to the AZ plus B over CZ plus D, which we denote by gamma Z. And if we let Z be infinity, and then we see that the same action also, applies to that. And its image will be all the rational numbers. So we put Q and together with infinity and view that as a P1Q. So there's also the action of SL2Z there. Okay. And we take a finite index subgroup of SL2Z called gamma. Okay. And the orbits of gamma on the P1Q are called cusps for the group gamma. Okay. And then and we look at the orbit of gamma on the upper plane, okay, and that usually is denoted by Y gamma, okay. So we can compactify it by joining the cusps of gamma, and then we get a Riemann surface, which we call the X gamma, and this is a modular curve, and it is a model defined over a number field. So gamma is called a congruent subgroup if one can define its entries using congruence relations. And an easy way to describe that is to say that a gamma contains a subgroup whose matrices are congruent to identity modulo some positive integer n, which we call a gamma n. This is called a principal congruent subgroup. And if it's not a congruent subgroup, we call it a non-congruent subgroup. Okay. So a theorem by Bas, Lazard, and Serre says that all finite index subgroups of SL and Z for n at least 3 are congruent subgroups. So SL2Z is very special in that not only that it contains non-congruent subgroups, but actually contains many non-congruent subgroups. So here's a way to see, I give you three ways to see that. Okay. First is a result by Lubatsky and Ziegel, where we sort the finite index subgroups by its index n inside SO2Z. Okay. And we count the number of them which are non-congruent subgroups and the count of number of them which are congruent subgroups. We look at this ratio, and they show that this ratio goes to infinity as n goes to infinity. And second way is by Theorem of Bay, which says that any smooth irreducible projective curve defined over a number field is isomorphic to a modular curve x gamma. And actually this group gamma, there are infinitely many choices. So they differ by conjugation. Okay. And we talk about the congruence subgroups. So it's known that this modular curve for a congruent subgroup is defined either over Q or over cyclotomic fields. Okay. So in comparison, you can see that there are tons of non-congruent subgroups. Okay. And the third way is to sort the modular curves by genus. Okay, so we will give a genus and we look at the gamma such that the X gamma has genus G, and only finite many gammas are congruent subgroups, but infinite many of them are incongruent, non-congruent subgroups. Okay. So next, I would like to give a modular interpretation for the affine curve Y gamma, so without cusps. Okay. So for the congruent subgroups, usually one considers three kinds. One is the principal congruent subgroup, gamma of n. The matrix is congruent to identity, mod n. And the second is called gamma 1n. The matrix is congruent to the upper triangular matrix, unipotent matrix. The third is gamma naught n, which is congruent to upper triangular matrix. And so we know that gamma n is a normal subgroup of, inside gamma 1n, and with quotient isomorphic to a z mod nz. And then gamma 1n is a normal subgroup of gamma naught n with quotient isomorphic to the multiplicity group of z mod nz. So it is very well known that it's also reviewed on Tuesday's lecture. Okay, so that if a gamma is a congruent subgroup, which is either gamma of n or gamma 1 of n or gamma naught of n, then this Y gamma parameterizes isomorphism classes of elliptic curves over C together with a suitable level structure. Okay, for example, if we look at just Y of SO2Z, then they parameterize the isomorphism classes of such elliptic curves. And it's Y of gamma naught of n, then parameterizes the elliptic curves together with a subgroup, a cyclic subgroup of order n. Okay. And if one choose a group to be gamma 1 of n, then the curve parameterizes the isomorphism classes of elliptic curves together with the point of order n. And if one chooses the principal congruent subgroup gamma of n, then the curve parameterizes the isomorphism classes of elliptic curves together with 2 points, P and Q. So they both have order n, and together they generate the n divisible points inside the elliptic curves, which is this product of 2 copies of Z mod nz. Okay, but it's not all such choices of PQ, but it's for the PQ such that under the Weil pairing, it is prescribed root of unity. So the wave pairing takes PQ to principal n through the 1. Okay, so we have to choose the principal root n through the 1. Okay, so if we fix the P, and then that restricts the choice of Q. Okay. So, so we know that this curve y gamma of n is defined over cyclotomic fields. Okay, joining n through the 1. Okay. So if we change the value of the pairing, then actually we get a curve which is over the Galois, defined over Galois conjugate. It's a Galois conjugate of this curve, so still isomorphic to that. So if we put them all together, then we get an object which is defined over Q. Okay. So this is for congruent subgroups. This is well known. Okay. And for non-congruent subgroup, the modular interpretation was worked out by Chen in his thesis, which is published in 2018. Okay. I see that Chen is also invited to give a talk. I think he will talk about his this result. So I will just give a quick introduction of what he did in this regard. Okay. So he first reinterpret the modular structure, say for the curves, so for the group gamma naught of n. We know that it parameterizes the isomorphism classes of elliptic curve together with the cyclic subgroup of order n. Okay, we call that group C. Okay. So another way to see that group C is that instead of C, we look at the E mod C. So we think of that as a parameterized E and isogeny from E to E mod C, or is a kernel, which is a cyclic of order n. Okay. And if we have isogeny from E to E mod C, then we can consider its dual isogeny. Okay. So dual isogeny means that I have a cover, Galois cover X over E, and with the Galois group isomorphic to Z mod and Z, the cyclic of order n. Okay. So this is the way he reinterpret the modular structure for the group gamma naught of n. Okay. So if we want to look at the modular curve for gamma 1 of n, we know that it parameterizes E together with the point of order n. So that means that inside, if I start with a cyclic group of order n, that means that we have to choose a generator inside this group. So therefore, we view that this modular curve y of gamma n as parameterized E, and together with its Galois cover from X to E with a Galois group Z mod and Z, then to get the alpha, which is isomorphism from the Galois group to Z mod and Z. That means that we make a choice of a point of order n. Okay. So after reinterpreting the classical the modular curve over the congruent subgroups this way, then his idea is that we are going to replace, instead of this abelian cover, we can replace it by non-abelian covers. Okay, and as such, then that it will have a ramification. Then he says that that's restrict the ramification to be only above the origin of the elliptic curve. Okay. So then when we look at the punctured elliptic curve, namely if we remove the origin from the elliptic curve, then look at the fundamental group, then this group is a free group generated by two elements, X and Y. Okay. So we need to put that point back to get a, well, relation of a commutator equals 1. Okay. So without that, then we get a fundamental group puncture. The elliptic curve has fundamental group, which is a free group in two generators. Okay. So that we take a G, which is a finite group generated by at most by two elements. Okay. So we consider the triples. It's the elliptic curve X and a connected Galois curve of E, okay, branched at most above the origin, and together with an isomorphism alpha from the Galois group to the group G. So these are all the Galois curves with the Galois group G, and with prescribed the ramification condition, and together with isomorphism to the group G. Okay. And then one take the equivalence classes of such triple, and he showed that it's a smooth affine curve defined over Q. Okay. So if we look at the algebraic points on this curve MG, then, well, then decomposes into finitely many kinetic components. And he showed that these components, well, are parameterized by the surjective homomorphisms from the free group F2 to G, but the modulo the inner automorphisms of G. Okay. And to each such kind of embedding, there's associated a finite index subgroup called a gamma phi of SO2Z, okay, such that the component parameterized by phi, well, is exactly the affine modular curve Y of gamma phi. Okay. And that Y gamma phi is defined over a number field. Okay. As you collect all phi, then you get the final object defined over Q. Okay. And moreover, if we look at the orders of the phi at the generator X and generator Y, and the phi at the product of X and Y, if the three orders are pairwise co-prime, then he showed that a gamma phi is a non-congruent subgroup. And so then such kind of modular curves Y of gamma phi, they are abundant. There are many of them. So in the sense that if we take any modular curve Y gamma, it is a quotient by some Y gamma phi. Okay. So when G is abelian, for instance, if G is two copies of a Z mod n Z, then the Y gamma phi is just gamma n. Or if it's one copy of a Z mod n Z, then this group gamma phi is a gamma 1 of n. Okay, so then when they are, well, they are congruent subgroups, but they are also non-abelian G, such that gamma phi is a congruent subgroup. For example, if G is dihedral, then he showed that so G is also, since gamma phi is also non-congruent subgroup. And then later, in joint work with the Lin, he showed that if G is a meta-abelian, this is also the case. So group is meta-abelian means that it has an abelian subgroup with abelian quotient. No, it has abelian normal subgroup such that a quotient is also abelian. So it is a step 2 solvable group. And he also showed that if we take G to be the symmetric group in at least 4 letters, or alternating group with at least 5 letters, or the PSO2 P with a P prime at least 5, So when G is like this, then the least one kinetic component of MG, well, is a non-congruence modular curve. Okay, so so I think Will will give all the details. I just give an overview of what he did.
Orders are not mutually coprime.
Pardon me?
The three orders, phi x, phi y, and phi xy,
Yeah.
are not mutually coprime. Even then, I guess in some sense, most of the time you get non-congruent subgroup.
In principle, yes. Yes.
It has to be made precise, yeah.
Because the non-congruent subgroups are abundant, and
Yeah,
he also shows that this kind of modular curve, so basically covers all the Y gammas. So most of them, are expected to be non-congruent. The question is that how to determine whether it's non-congruent or not. Okay. So now we go to modular forms. Okay. So on this modular curve, let's take a holomorphic differential, fz dz. And then for this f, and it has the following properties. First, it's the holomorphic function on the upper plane and also a holomorphic at the cusps. And the second is that this differential is invariant under the action of a gamma. So that means that f of gamma z d gamma z equals fz dz. Okay. And when you look at a d gamma z, you find out that it is 1 over cz plus d squared times dz, where the gamma has a second row in the cd. Okay. So that means that f gamma z times cz plus d to the minus 2 is equal to f. So that's the symmetry that gamma, the function f, has to satisfy. And the third condition is that f vanishes at the cusp of gamma. Okay. So it's from this holomorphic differential, we generalize this idea to define a modular form. So we say a modular form, first it should be holomorphic on the upper plane, and it should and also at the cusp. And for the second condition, we relax this 2 by replacing it by integer k. Okay, so if that's the case, then we say that this f is a modular form of weight k for the group gamma. Okay, and for the convenience, this expression cz plus d to the minus k times f gamma z, we will denote it by the f stroke gamma. Okay, and if this form also vanishes at a cusp, then we say that it's a cusp form. Okay, and the collection of the modular forms of weight k for gamma form a finite dimensional vector space over C. Okay, so we call that space mk of gamma, and certainly the cusp forms inside it form the subgroup sk gamma. Okay. And the complement of the cusp forms inside the all modular forms, well, for them, they are explicitly constructed with K-Eisenstein series. Okay, so they generate a space which complements the sk gamma. So we consider the Eisenstein series well known, and so interested in the cusp forms. Okay, so in view of this definition here, then we go back and look at the FZDZ. Okay, so we start with this holomorphic form, holomorphic differential. That another way to say that is that the f of z is a cusp form over 2 for the group gamma. So this shows that the dimension of a space of with 2 cusp forms is equal to the genus of the curve. Okay. So in this the action of the group, okay, one noticed that if the matrix is a translation, then actually the stroke operator, well, just is equal to F itself. Okay. So in other words, modular form or cusp form is invariant under some translation because the group gamma has finite index inside SL2Z. So that means that as a function on the upper plane, it is periodic. Let's take the smallest period. Okay, the smallest period actually is the width of the cusp at the infinity. Okay, so then we can write F in the Fourier expansion with respect to e to the 2 pi I z over mu, then raised to the powers. Okay, so traditionally we denote e to the 2 pi I z by q. Okay, so we can write this fz as the series over some constant Fourier coefficients times q to the n over mu. Okay, originally it should be from minus infinity to infinity. Yeah. But since this q to the 1 over mu is a uniformizer at the cusp infinity, and f is holomorphic there, so the series starts with 0. And here we start with 1 because f vanishes at the cusp infinity. Okay. So, well, what we're interested in is the arithmetic properties of the Fourier coefficients of cusp forms. Okay. So the first example is also the most well-known example is the Ramanujan's tau function. Okay, so that's for if we take the group to be the full modular group, and the first cusp form has the weight 12, so that's the lowest weight. Okay, and in this case, the space is one-dimensional, generated by the so-called discriminant function. This discriminant, they denote discriminant for elliptic curves. Okay, and Jacobi showed that this suitably normalized the discriminant function can be expressed as q times the product of 1 minus q to the n raised to the 24th power. When we expand it, we get this q expansion for the gamma z. And we can see that all the coefficients are integers. Okay. And Ramanujan is interested in this because this infinite product part here is related to the generating functions of the partitions. Okay. So he computed about 30 Fourier coefficients for delta. And in 1916, he came up with the following conjectural properties about the Fourier coefficients of tau n. The first is multiplicative. That means that tau viewed as arithmetic function on positive integers. So if the argument is a product of 2 co-prime integers, then tau m and n, then tau mn is tau m times tau n. So this means that to understand the value of tau, it suffices to know tau at the prime powers. So then we fix the prime power p. Then the second is that for the gamma, for the coefficients in primes of p, at primes of p, they satisfy a 3-term recursive relation relating tau p to the n plus 1 at the p to the n and the p to the n minus 1. Okay. And so in front of tau p to the n, there's a minus tau p, and then in front of tau p to the n minus 1 is the p to the 11. So 11 here is the weight minus 1. Okay. So with these two conditions together, that means that if we know the value of tau p, then we will know all the Fourier coefficients. Okay. The third statement is about the size of a tau p. There's a famous Ramanujan bound. says that it has absolute value bounded by twice p to the 11 over 2. Okay. So the first two statements were proved by Model and the last one proved by Deline. Okay. So this example actually showcases the many key properties we will touch upon for congruence modular forms. Okay. So the first one is that we notice that its delta has Fourier coefficients or in integers. Okay. So in general, if we take a congruent subgroup, and one can show that the space of a cusp form, so weight k for gamma has a basis with the algebraic integral Fourier coefficients. Okay. So consequently, if we have congruence modular forms and with algebraic Fourier coefficients, then the denominators are bounded. Okay. So for a non-congruent subgroup, the study is initiated by Atkin and Swinton Dyer in 1971. And so when we talk about arithmetic Fourier coefficients, we will always assume that the curve has a model over Q such that cos infinity is a Q rational point. So that's the only, that's the case that's been investigated. Okay, so in this case, ASD and show that so there is an integer m which depends only on the group gamma, such that the space of cusp forms of weight k for gamma has a basis which are integral with which have Fourier coefficients integral outside the m. Okay. So for non-congruent subgroups, this m here more or less plays the role of the level for the congruent subgroups. Okay. So here, let me give you one example of a non-congruence modular form. Okay. So let's consider the Fermat curve, x cubed plus y cubed equals z cubed. So it is also an elliptic curve. Okay. So by Bayes' theorem, we know that this E is, well, isomorphic to modular curve. In this case, this one knows that this group gamma is an index 9 subgroup for of gamma 2. Okay. This elliptic curve has genus 1, so the weight 2 cusp forms the space is one-dimensional. And we can explicitly compute a generator alpha z. So as shown here, as you see that it's an integral except at 3. And you also see that the powers of 3 in the denominator, well, goes up very quickly. So it's an unbounded denominator. So then it's a general question. Is that if we give ourselves a non-congruent subgroup and we consider the weight k cusp forms for it, okay. So inside here, it may contain modular forms for congruent subgroups. For instance, may come from modular forms from SL2Z, okay. So how can we tell whether a form is from, if a form has algebraic coefficients, Fourier coefficients, whether it is from a congruent subgroup or non-congruent subgroup? We saw before that if it's coming from congruent subgroup, then it will have bounded denominator. So then it's a folklore conjecture saying that this must be a necessary and sufficient condition. So that's the way to distinguish congruence forms from non-congruence forms. Okay, so it's called the unbounded denominator conjecture. So it was finally proved by Frank Caligari, Dimitrov, and Chen. And I also see that Dimitrov will give a talk on their work related to this conjecture. But this is a very nice and a very clean conjecture. Okay. Very nice and clean criterion for non-congruence forms. Okay. So now we go to the cusp forms for congruent subgroups. I want to take a closer look. Okay, so we saw that gamma 1 of n is a normal subgroup of gamma naught of n. So gamma naught of n will act on the space of cusp forms for gamma 1 of n. And because the quotient is isomorphic to the multiplicity group of Z mod NZ, so the representation space decomposes according to the irreducible representations of this group, which means it's a character. So as we decompose it according to the irreducible representations, so then this space SK gamma will consist of a cusp forms for gamma 1 of n, such that when you hit a bound by an element from gamma naught of n, whose right lower corner is d, then you get a chi of d times f of z. Okay. So such kind of form we say has a weight k, level n, and a character chi. Okay. So if this space S k and chi has a non-zero form, then there's some parity matching. So chi of -1 should equal to -1 to the k, and also means that the conductor of chi should divide n. Okay. So then here we can define the so-called diamond D operator. Okay. So we give ourselves any integer d, which is a coprime to n. And the diamond D operator will take f to the f stroke gamma for any gamma in the gamma naught of n, such that the right lower corner is d. Okay, and clearly it's independent of such choice. Okay. So the diamond D acting on this space SK and chi is just multiplication by chi of d. And another important thing I want to talk about is about the cusp form for the principal congruent subgroup gamma n. So we know that its Fourier expansion is in powers of q to the 1 over n. Okay, so if we change the variable from z to n times z, then the Fourier coefficients will be in powers of q. And the Fourier coefficients we don't change, but the powers of q looks simpler. Okay, then this fnz becomes a form for the conjugate of gamma of n. That group is conjugated by the matrix n0, 0, 1. So if you look at the product of a matrix from gamma of n by conjugate by n0, 0, 1, you see that the net result is that the n multiplied to b gets moved to the C corner, lower left corner, and all the other entries, ABD, remain fixed. So, and such kind means that we are looking at a new congruent subgroup with the level will be n squared here, but the AD corner will be the integers which are count to 1 modulo n. So that means that that group, the forms for that group will decompose as SK n squared chi, where chi runs through the characters of n mod, z mod, nz cross. Okay. So this is a very convenient isomorphism, and this isomorphism means that, well, to understand all the cusp forms for congruent subgroup, it suffices to understand to study the space SK and chi. Okay, and also when chi is a trivial character, then that space becomes the K modular forms for gamma naught n. Okay, so then we will include all the major congruence forms. Okay. So then we come to the properties of Ramanujan's conjecture A and the B. Okay. So to form in S of weight K level n and character chi, we write its Fourier expansion. We use the Fourier coefficients an to form the associated L functions. Okay. So if we do this to the Ramanujan delta function, the conjectures A and the B tells us that we can rewrite this L function as a product over the primes, which is we can separate the primes. That's the A part. And the B part is the recursive relations that's expressed as 1 over 1 minus tau p times p to the minus s plus p to the 11 times p to the minus 2s. Okay, so then, so the L function attached to Ramanujan's function is very neat, okay, expressed in this way. So in general, we ask more humble question. Okay, if we take this L function attached to F, we say that it's Eulerian at the prime P. If we can separate its L function for the co-prime to P part from the P part. So the P part here, we just have a series in powers of P to the minus S. Okay. So we ask when this can happen. So to answer this question, Hecke introduced the Hecke operators. Okay. So for any finite index subgroup of SO2Z, we can take the double coset of 1, 0, 0, P with both. We take 1, 0, 0, P, multiply both sides by the group gamma. And one can express this double coset as the union of the gamma cosets, okay, with the finite many representatives, gamma j. And the action of a Hecke operator on the weight K cusp forms, so gamma, is just by applying this averaging on the coset representatives. So here we have our suitable normalizing constant in front. Okay. So if the group is a gamma 1 of n, then usually if a P is co-prime to n, and then one knows that they are P plus 1 cosets, gamma cosets, and usually one chooses representatives to be 1 U0 P, where U is integers modulo P, and another one is a diamond P times P001. And the effect of a Hecke operator on cusp forms of weight K level n character chi reflected on its Fourier coefficients is that then the nth coefficient will becomes A and P plus chi P times P to the K minus 1 times A n over P. Okay. So on the congruence forms, okay, if we look at the space Sk and chi, and Hecke showed that if a form is Eulerian at the prime P not dividing n, it's equivalent to this F being an eigenfunction for the Hecke operator. And as eigenfunction then has eigenvalue, that's called a lambda P. So in other words, the associated L function, we can really separate the non-P part from the P part. And the P part also, well, has a nice recursive relation. It's 1 over 1 minus lambda P, P to the minus S, lambda P is the eigenvalue, plus chi P, P to the K minus 1 times P to the minus 2S. Okay. So another way to say this is that the Fourier coefficients of f satisfy the three-term recursive relation between a and p, a n, and a n over p. So the coefficients in front of a n and a over p comes from that is the denominator here minus p for a n and the chi p to the k minus 1 for a n over p. Okay. So one can show that on the space of S k and chi, the operators, each Hecke operator is diagonalizable for p not dividing n, and they commute with each other. So that means that they can be simultaneously diagonalized on this space. Okay. So if we look at the Hecke operators we just defined on the non-congruence forms, okay, the story is very different. So if gamma is a non-congruent subgroup, we denote by gamma c, it's a non-congruence closure, so which is the smallest congruent subgroup containing gamma. Okay. So Atkin had conjectured that so the Hecke operator will give no information on the genuinely non-congruence forms. Okay. So this was actually first studied by Sayre for the group where gamma is a normal subgroup of SL2Z, and then completed by Berger for all the non-congruent subgroups. Okay, so let's look at these coset representatives gamma J for the TP defined using the as we define here, using the double coset definition here. So they analyzed the coset representatives, okay, and found out that the TP defined that way actually means the following. So first, we take the trace from the cusp forms for gamma to cusp forms for gamma C. Okay, so gamma C contains gamma. Okay, so the forms for the larger groups certainly are the forms for the smaller groups. And the trace means that you take the coset representatives of the gamma inside gamma C, then you average the forms for gamma by the coset representatives to make them a form for gamma C. Okay. And then followed by the usual Hecke operator on the congruent subgroup gamma C. Okay. So now this trace map, when you restrict it to the forms formed for the gamma C itself, it is multiplication by the index. Okay. Okay. So both sides are finite dimensional vector space, and it's a surjective map. So this forms for gamma C means it's exactly the congruent subgroups. Exactly the congruence forms contained inside this space SK gamma. Okay. So the kernel of this trace map are precisely the genuinely non-congruence forms. Okay, so this shows that the genuinely non-congruence forms are sent to 0 in the trace map. So this is why the Hecke operator gives no information on the genuinely non-congruence forms. Okay, so that is the main handicap to studying the arithmetic for non-congruence forms for non-congruent subgroups. Okay, so from now on, I'm going to talk about the congruence modular forms for quite a while. And then after it's done, then I will talk about what we know for the non-congruence modular forms. Okay. So on this space, SK and chi, we have the Hecke operator for P not dividing n. And for P dividing n, we have the UP operator. So that is just taking the first P representatives for the Hecke operator. And then takes a form with Fourier coefficients an in front of q to the n to a form with Fourier coefficients a and p in front of q to the n. Okay. So these operators up for p dividing n, and TP for P not dividing n, and also the diamond operator D for integers modulo coprime to n, and we take them modulo n. So they commute with each other. So they generate the Hecke algebra on the space of the cusp forms with K for gamma 1n. So now I'll talk about the theory of new forms. Okay. So the purpose of the theory of new forms is to describe the structure of a congruence cusp forms with a fixed weight K and the variant levels. Okay. So it started by the paper by Atkin Lehner, where they collect all the congruence subgroup gamma naught n, put them together, and to see how the modular forms relate to each other. And then Miyake did that for the group gamma 1 of n. So to get the information for all the congruence forms, certainly we need to know the information for gamma of n. Okay. And it's seen from the paper by Atkin and Lehner, it's clearly they also consider the similar thing for the gamma of n. And they clearly discovered that it will not work if we just collect SK of a gamma of n and put it together. The theory will not work. Okay. So what I figured out is that in view of the remark I made earlier, that the modular forms for the gamma of n, it's really by putting together modular forms of level n squared and a suitable character chi. Okay, so realize that the right way to look at this all modular forms is actually we should fix k and a fix chi and the very n and put that together and to see how things work. Okay. So there are two facts. So the first is that if I take a level m, which is a proper divisor of n, so the group is larger. So a form of a lower level m here certainly is also a form for n, which is a multiple of m. But not only we can put a g in there, we can also change the variable, replacing z by d times z for all the factors of n over m. Okay. So for one g with a lower level, we actually produce several forms coming from g, and we call this a g dz is a push-ups from the g. Okay. And moreover, if g itself is a eigenfunction of Hecke operator Tp for p not dividing n, and with eigenvalue lambda p, then so are all the push-ups. Okay. So from the viewpoint of the space S, K, and chi, all these forms coming from lower levels, they are called, they generate a space called the old forms because they are forms of lower levels. Okay. So we remarked earlier that the space as SK and chi decomposes into a direct sum of common eigenspaces for the Hecke operators P with P not dividing n. Okay. So we similarly, this works for the SKM chi. So if G is a common eigenfunction there, and then by the remark, you also see that so are its push-ups. So that means that and for that common eigenspace, it will have dimension greater than 1. Okay. And a very key theorem in the theory of new forms is that when we decompose this Sk and chi into the right sum of a common eigenspaces of Hecke operators, then those with a dimension greater than 1, if and only if all the forms, or if and only if that that space actually is generated by all the old forms. Okay. So that means that the only thing we have not touched upon are the common eigenspaces, which is one-dimensional. So so the forms in that one-dimensional common eigenspace, well, are not coming from old forms, so they are called a new form. Okay. So from this point of view, so if we lump together all the levels n with a fixed k and a chi, that means that this big space, well, has a structure that it has a basis consisting of a new forms with k character chi and all kinds of level, and as well as their push-ups. Okay. So to understand the congruence modular forms, it suffices to understand a new form of a given level. Okay. So now let's take a G to be a new form of a level n. Okay, character with k and the character chi. So let me summarize the main properties of the this new form.
Who proved this theorem?
Pardon me?
Who proved this theorem that dimension is greater than 1 if and only if?
This is the result of all. It's in Atkin-Lehner for the group Galois, and it's Miyake also in my paper. That's the key thing about the theory of new form. Okay.
Did Rankin prove something in this direction?
Who?
Rankin?
Rankin? I don't think so.
Okay, okay.
So the first property is that the leading Fourier coefficient A1 is non-zero. Okay, so since it's non-zero, we can normalize it, assume it to be 1. So usually when people say the module take a new form, you start it with 1, blah, blah, blah. But it's not automatic that the leading coefficient is non-zero. Actually, it requires quite a bit of proof to show that it is non-zero. Okay. And the second is that coming from the construction that G, well, is an eigenfunction for all the Hecke operators with P co-prime to n. Okay. And with the eigenvalue is AP once we normalize the leading coefficient. Okay. And since this common eigenspace is generated by G is one-dimensional, and so if we take a P dividing n, the UP acts on this space. So G certainly is also an eigenfunction of a UP, okay, with eigenvalue AP. Okay. So that this reflected on the its L function means that its L function has Euler product everywhere at the prime P not dividing n, and the factor is 1 over 1 minus AP times P to the minus S plus chi P to the K minus 1 minus 2S. And that prime P dividing n is 1 over 1 minus AP P to the minus S. So again, all the APs will determine the Fourier coefficients of G. Okay. Then let me talk about the what we know about the Fourier coefficients at the bed primes P dividing n. Okay. So if chi is not a character of n mod P, then one knows that the size, the absolute value AP is P to the K minus 1 over 2. Okay. Now, if chi is a character mod n over P, And if p squared does not divide n, then one knows the AP squared explicitly is chi p times p to the k minus 2. So again, the absolute value AP is p to the k over 2 minus 1. It's smaller than in the size and smaller than the previous case. Okay. But if the p squared divides n, then the AP is equal to 0. Okay. And the size for the Fourier coefficients AP at the p not dividing n, so there's a famous Ramanujan conjecture, and now it's proved. We call that Ramanujan bound. It's bounded by twice p to the k minus 1 over 2. Okay, so as you can see that for the p not dividing n, the key thing is p to the k minus 1 over 2. At the p dividing n, the absolute value is either well, it's also bounded by that. Okay. Another property is a strong multiplicity one. So if we take another normalized new form of the same weight, but the level n prime and character chi prime, and such that the eigenvalues Cp is equal to AP for almost all primes P. Okay, if that's the case, then H is actually equal to G. Okay, so in other words, if we take two new forms, two distinct normalized new forms of the same weight, then the Hecke eigenvalues should be different at infinitely many primes P. Okay. And all the Fourier coefficients are algebraic integers. If we put together, they generate a finite extension of G. Okay, so if the character is trivial, then actually all the Fourier coefficients are real. Okay. And another property is that if we take an element from the Galois group of a Q bar over Q, okay, so we apply that to the Fourier coefficients because Fourier coefficients are algebraic. Sorry. And then the resulting form thing is also a new form of the same weight, same level, but the character becomes the conjugated by sigma. Okay. And the final property I will talk about it's the analytic property of the associated L function. So originally defined as Euler product, it's converges absolutely for a real part of S large enough. And in fact, it can be analytic continued to the whole S plane and holomorphic everywhere. So it's an entire function. It's bounded in each vertical strip of finite width. And there's a symmetry. So this satisfies a functional equation, which relates modular form G with modular form we call the G bar, whose Fourier coefficients are complex conjugates. This one we know that if we take a sigma to be the complex conjugation, then we get a new form with a character which is a chi bar. Okay. And the variable S and the variable K minus S. So to describe this explicitly, we need to complement the L function by a gamma factor. So for holomorphic modular forms, the gamma factor is 2 pi to the minus S gamma S. Okay. And that product, we call it lambda. So lambda GS is related to lambda G bar K minus S. And in front of it is the level N to the K over 2 minus S. Okay. And the times are a constant, a non-zero constant. G. Okay. So I think I will stop here. And so all these analytic conditions, so together we call this A of G, A's analytic condition for the G. This G is the same as that G. Okay. So I will stop here for today.
Thank you, Winnie. So let's give Winnie a virtual thumbs up or clap.
Thank you.
Are there any questions?
What are the references?
Reference?
Yes. There books or papers or
Oh, there are quite a bit. Okay. So for the non-congruence forms, and there are all papers. For the congruence forms, I think there are many forms for modular forms.
for the non-congruence forms.
For non-congruence forms, there's no books, there are only papers.
So there's a question on the chat, Winnie, from Aniruddha. In the strong multiplicity theorem, how is it seen that the levels are the same? Why can't the forms be twists of each other? What happens in that case?
How is it seen that the levels are same?
The levels are the same. Yeah.
Yeah. So I actually gave a proof for this strong multiplicity one theorem in my book called the New Number Theory with Applications. So my proof is that I actually use this functional equation. So I take the lambda for G and the lambda for H. So we can compare the quotient because we know that it has the Euler factors at almost all primes P. So eventually it's a product over the finite thing. And so then the level shows up in the functional equation. And from there, you can argue that what I just said. So one proof of this fact is in my book, Number Theory with Applications, published by World Scientific.
May I ask a question?
Yeah.
Please go ahead.
So in strong multiplicity one, you also assume that H has the same weight as F, right? What if we take the different weight here?
Okay, so for different weight, actually, you can see the, say, for instance, the functional equation will have different type, and also the Fourier coefficients are of different sizes. You see, the size is the bound that depends on the weight. So
Okay.
certain,
Yeah, please.
Yeah, go ahead.
Okay, so can you please go to the previous slide, slide 24?
yes.
I'm sorry, I could not understand this theorem which you mentioned on the first line. So, I mean, for example, if we take just say, for example, delta Z and delta 2Z, so they have the same, they lie in the same common eigenspace, right? But the space, okay, yeah, I'm sorry. Okay, I was confused now. Now it's okay. Thank you. Okay.
So if it count, so this first says that if the common eigenspace is one-dimensional, then it doesn't contain any odd forms, and if it's the eigenspace is has dimension greater than one, then everybody there is odd form. Yeah.
Yeah. Thank you.
Winnie, I had a question about the Ramanujan bound. The theorem that you know. So is that also due to Deligne, or is it a more subtler proof for this one?
So I will talk about that in part 2.
Okay.
So it's a consequence of a Galois representation attached to the modular form. Okay. So weight 1 is the Linsayer, weight 2 is actually Eicher-Schmura, and for higher weight is Deligne.
Okay. So if there are no other questions, let's thank Winnie again. And we look forward to her next lecture. Thanks, Winnie.
Thank you.
Okay, so I suppose, I don't know, Devendra or whoever is in charge, you take over now, right?
Are there, so there's, I mean, the chat disappears. So
Well, there seem to be no other questions on the chat apart from these. So, I mean,
yeah, sorry,
related to
I
lecture.
Yeah, I
Go
didn't
ahead,
read
Sujata,
it
for
well.
coming to chair this talk.
Yes.
And
Thank you,
Luca,
sir.
maybe you can stop the live stream.
Sorry.
Are they-
Yeah.